In this segment, we will predict the products from the given reactants and write the full formula reaction equation, but this time for single replacement reactions in aqueous solution. Some textbooks wait until a later chapter to discuss this type of reaction. Sometimes it is included as part of a lab experiment. For many double replacement reactions, you can determine whether or not a reaction will occur by seeing whether a net ionic equation can be written or whether all substances in the reaction cancel out. For single replacement reactions, on the other hand, we cannot use those criteria to determine whether a reaction occurs. What will be needed to determine whether a single replacement reaction occurs is the activity series or standard reduction potential tables. Because those topics are likely to be covered only later in your course, we will use examples here assuming that you know or are told or see that these do undergo reaction. This slide compares double and single replacement reactions. In part 1 of this series, we noted that the most obvious difference between these two types is that the double replacement reactions are reactions between two compounds, and the single replacement reactions are between a compound and an element. We discussed double replacement reactions in part 1. So what happens in a single replacement reaction? In a single replacement or single displacement reaction, the element becomes part of the compound, and the ion replaced in the compound becomes its elemental form. Because the atoms interchanging between element and ion form are changing charge, this is an oxidation-reduction reaction. In other words, electrons are gained or lost. Not all oxidation-reduction reactions are single replacement reactions, but single replacement reactions are always oxidation-reduction. Here are some examples of single replacement reactions. The copper 2 nitrate and zinc element. Zinc solid is the element form. So we're going to be taking the element form and placing it in the form in which it would exist in the compound, which would be as its ion, zinc 2+, and the copper will become the element. Here's the way you would express that answer. Chlorine and sodium bromide. Chlorine element would form chloride minus ions instead of plus ions, so it will replace the element in the compound, that is, the minus ion. So chlorine becomes chloride, and the bromide becomes bromine, its elemental form. This needs to be balanced to keep the equation complete and fully balanced. Now we'll do one that is a little more detailed. Here's a slightly trickier one. Sodium solid, that's sodium metal, and water. This is an element, sodium metal, and a compound, so we are considering single replacement. First, let's look at the ions present in the compound water. Even if they are only present to a minor extent, as we did see also with the ammonia and water in part 1. Okay, what ions are present? The ions are OH- and H+. Water is a very polar compound. It has partial plus on the H and partial minus on the O. And one of those bonds between H and O might break off, leaving H as plus, the pair of electrons on the O, meaning OH- is left. So H plus and OH- are the common ions you'd expect, even though they're in very small quantity. In neutral water, it's 1 times 10 to the minus 7th molar for each. But all we are looking for here is what ions. They don't have to be the major form because we're not writing them into the balanced reaction. We're only looking for how water might react. Okay, sodium has a 0 charge. We know that sodium commonly forms +1 ions. In order to get from sodium to sodium +1, sodium has to lose an electron. That's why single replacement reactions are oxidation reduction. Loss of electrons means oxidation. So it's losing an electron. The electron is going to go to the comparably charged atom of the other compound. So H plus is going to become H neutral, but we know the formula of H atoms doesn't exist much in nature. What we're going to have is H2. That means we have to take 2 sodiums, giving up 2 electrons to make 2 sodium ions and 1 H2. So let's look at this as part of our product now. The H plus in water is going to go to H2, but both of those came from the H's. So that means that we need to keep a total of 2 waters. Did we get that? The H plus went to H2. That took 2 of the H ions, which meant we had to have 2 OHs and 2 H pluses. These two became that. Now we have OH minuses left. 2 in front of the Na plus here means that we have 2 Na pluses. You see what we now have is sodium hydroxide as our product. 2 molecules of sodium hydroxide, or overall what we see is the sodium hydroxide with a 2 in front. By the way, in this reaction, so much heat is given off in the reaction that the sodium melts and may ignite the hydrogen gas or cause an explosion. If you like seeing explosions, there are many videos on YouTube of sodium or other alkali metals reacting with water. In other words, don't do this reaction at home. On this slide, I have listed the steps we have followed. You can pause the video to review it if desired. Some of the slides from this presentation are available, as well as some additional problems with solutions that include bits of all the topics from all the videos on writing full formula, complete ionic, and net ionic equations.